In the last video we examined Thomas Kuhn, and we saw that Kuhn's central idea is that scientists adopt paradigms, which are whole ways of doing science, whole ways of thinking about the world. Kuhn's model is that we have normal science governed by a single paradigm, where anomalies build up, which eventually leads to crisis science, where scientists lose confidence in the paradigm, and then to a revolution, where one paradigm is replaced by another and normal science resumes. Now, I mentioned that according to Kuhn, competing paradigms are incommensurable, which basically means that they have no common measure by which to compare them. In this video, we're going to examine the notion of incommensurability in a bit more detail, because this is one of the most important and most controversial aspects of Kuhn's work. Now, the concept of incommensurability can be broken down into three key ideas, and all of these are quite important. There is methodological incommensurability, observational incommensurability, or the theory-ladenness of observation, and semantic incommensurability. So first of all, let's talk about methodological incommensurability. This is basically what I've mentioned before. This is the claim that there are no independent standards for evaluating competing paradigms. Each paradigm supplies its own standards of evaluation, and we can't step outside of paradigms to find the objective standards. So paradigms have different methodologies, and therefore you have no common way in which to evaluate them. A nice example of this is the theories of gravity. Initially, a problem for Newton's theory was that it viewed gravitation as involving action at a distance, with no explanation or mechanism provided. Gravity was treated by Newton as this brute basic force. He didn't explain how the force was exerted. And this seemed very spooky and mysterious to scientists of Newton's time, who adopted a mechanistic approach, where causes are always linked mechanistically to effects. The general attitude at the time of Newton was that science should provide mechanistic explanations. A competing theory of gravity was offered by Descartes. We don't need to go too much into the details here, but Descartes held that all of space is filled with a very fine matter. There's no truly empty space. This matter tends to form circular motions, which produce large vortices. Centrifugal force pushes the fine matter to the outer edge of the vortex, so the fine matter accumulates at the outer edge. Objects that have a larger mass, such as planets, they don't follow due to the greater inertia, so that the fine matter accumulates at the outer edge, and the pressure of this fine matter pushes the planets inwards. This inward pressure is gravity. That's Descartes' idea in brief, and you can see that. So for him, he's got a mechanistic explanation of how gravity works. And for many scientists in the 16 and 1700s, Descartes' theory in terms of vortices seemed superior, at least in the respect that it provided a mechanistic explanation. I mean, certainly it was regarded by many people to be a serious problem for Newton that he didn't supply a mechanism. However, Newton's theory gave more accurate predictions, which led to its triumph over Descartes. Now, the interesting thing for us is that once Newton's theory became accepted, the fact that it postulated no mechanism was no longer taken to be a problem with it. Instead, scientists simply dropped the methodological requirement that scientific theories should provide mechanisms. And indeed, later scientists actually took Newton's work as a model, as an exemplar, as Kuhn would say. The Stanford Encyclopedia of Philosophy article on this cites the case of Coulomb's law, which describes the force between static electrically charged particles. In its form, it resembles Newton's law of gravitation, and like Newton, there was no suggested underlying mechanism for the force of electrostatic attraction. In this respect, the very similarity of Coulomb's law to Newton's was taken as a point in Coulomb's favour. So we see how a feature that was originally a problem for Newton became a virtue due to these changing methodological, due to these changing standards. So Newton's theory became paradigm, Newton's law of gravitation became an exemplar against which later work was judged. And the problems for Newton's theory were removed, not by solving the problems, but just by removing the kind of methodology that produced those problems. So, I mean, Newton was more predictively accurate than Descartes, but Descartes provided a mechanistic explanation. What's more important, predictive accuracy or explanation? These are competing standards. Predictive accuracy triumphed over explanation, at least for a time, but did that have to be the case? It seems like scientists could have adopted different standards, and it's not clear that this would have been irrational. Now, in later work, Kuhn did allow that certain standards are widely accepted and shared even across paradigms. And he gave 5 of these. He says that theories, all scientific theories must exhibit accuracy, so correct predictions. They must exhibit consistency, both internal consistency and consistency with other accepted theories. They must have scope, which means that they must explain phenomena, and it must be possible to extend them to explain phenomena beyond those for which the theories were originally developed to explain. Theories must be simple in some sense or another, and they must also be fruitful for further research. Now, although these criteria are widely shared, they don't quite solve the problem of methodological incommensurability because they are very imprecise. There's no algorithm to determine whether or not a paradigm is simple, for example. Simplicity is quite a vague concept, and we can define it in different ways. Also, we can disagree about how these virtues should be weighted. With the example of the debate between Newton and Descartes, the Cartesians certainly cared about predictive accuracy. They just felt that explanation was also very important. So we will often find that when evaluating theories, these virtues conflict. So methodological incommensurability still holds even when scientists might seem to share the same standards. A rather more radical idea related to incommensurability is observational incommensurability, which is more commonly known as the theory-ladenness of observation. The basic claim here is that the theories you accept alter the way you see the world. So, standardly, we tend to think of observations as providing a kind of neutral arbiter between theories. One theory predicts that under certain conditions we will observe X. Another theory predicts that under those conditions we will observe Y. We make the observation, and this supports one or the other of these theories, or maybe neither. But it's a straightforward matter to determine which theory an observation supports. That's the usual way we think about observations. But according to Kuhn, the observations we make are dependent on the theories we accept. So observation is not a neutral arbiter. Theories, to some extent, determine our observations. A simple example that's often used to illustrate this is this famous duck-rabbit image. This image can be seen either as a duck or as a rabbit. So if I say to somebody, hey, look, here's a picture of a duck, they'll see it as a duck. If I say, here's a picture of a rabbit, they'll see it as a rabbit. Our expectations about the world influence our observations of it. Norwood Russell Hansen has a nice example. He says, suppose that Tycho Brahe and Johannes Kepler are watching the sunrise. Brahe held that the Earth was the fixed centre of the universe. Kepler, of course, held that the Earth orbits the sun. So Hansen says that when they're watching the sunrise, Tycho sees the sun rise up above a stationary horizon, whereas Kepler sees a moving horizon dip below a stationary sun. Or as Hansen put it, there's more to seeing than meets the eyeball. Kuhn had a nice example. He says, looking at a bubble chamber photograph, the student sees confused and broken lines, the physicist a record of subnuclear events. Now, in defence of this view, Kuhn appeals to evidence from what's known as the New Look tradition in psychology. So in a famous experiment reported by Jerome Bruner and Leo Postman in their article On the Perception of Incongruity, subjects are rapidly exposed to 5 cards and then asked to identify them. Now, 4 of the cards are cards that you'd find in any standard deck. One of the cards is anomalous, so a black 4 of hearts, for example. Obviously, a normal 4 of hearts would be red. Now, generally, subjects are able to correctly identify the standard cards, but they fail to notice the anomalous cards. Instead, they fit the anomalous cards into prior categories. So rather than seeing a black 4 of hearts, they claim to see a black 4 of spades. And Kuhn took this to show that how we see the world is dependent on our theories and expectations. Similar results have been obtained from more recent studies. In a study by Richard Gunstone and Richard White in their article Understanding of Gravity, students were shown 2 balls. There was a heavy metal ball and a light plastic ball. They were first asked which of these balls would fall the fastest, and they were then shown the balls fall and asked to record their observations. The students who expected the heavy ball to fall faster than the lighter ball were more likely to report seeing the heavy ball fall faster. So the prior expectation that the heavy ball would fall fastest influenced their observations. So there is no theory-neutral observation, and that means that observation is not the neutral arbiter of theories. Even if paradigms had shared standards, we would not be able to use evidence and logic alone to decide between them, because the evidence is literally different for different paradigms. When 2 scientists of different paradigms look at the same phenomena, they see different things. So we can't use observations as this neutral arbiter between paradigms. Scientists who adopt different paradigms literally see the world differently. And that, of course, means that the decision to adopt a new paradigm isn't entirely rational. In crisis science, the data can't settle the matter because the data is determined partially by the theories under consideration. Science isn't simply a matter of judging theories against evidence. So, let's think about some responses to this. This is quite a radical idea. How might we respond? Well, first of all, we might argue that the evidence from psychology certainly shows that some observations may be altered by theory, but it might still be the case that there are plenty of neutral observations. To show that there is no theory-neutral observation, we would need to show that all observations are altered by theories, and that goes far beyond what the psychological evidence supports. Indeed, Jerry Fodor, in his article Observation Reconsidered, argues that empirical evidence shows that many perceptions remain unaffected by theory. And the best examples to illustrate this are illusions. Here's the Muller-Lyer illusion. You will notice that the top line appears to be longer than the bottom line. In fact, both lines are of the same length. Now, this is a very famous illusion. It's very well known among psychologists. There are many people who've known about it for decades and who've worked on theories explaining it and so on. But no matter how well educated you are on psychological theory, no matter how long you've known about this illusion for, the illusion remains. The observation that the top line appears longer than the bottom line is unaffected by your knowledge that the lines are the same length. And the same, of course, is true for many other kinds of illusions. And this suggests that theory doesn't penetrate into observation quite as much as Kuhn suggests. It seems that there are observations that are not influenced by the theories we accept. A second response is to note that the psychological experiments that Kuhn appeals to involve rapid exposures to the data. The participants are therefore provided with very poor information. But that's not usually the case in science, which usually involves carefully scrutinising large quantities of evidence. So if you let people look at the cards carefully, they can quite easily see that the black 4 of hearts is anomalous. They easily identify it as a black 4 of hearts. And so it's not clear that we can draw conclusions from these experiments and apply them to the sciences. In particular, we now use various instruments and techniques to eliminate any ambiguities that arise from perceptual limits. So, with respect to scientific instruments, imagine watching a horse race with a very close finish. You think that Frank won the race. I think that Vincent won the race. Well, the slow motion film of the race can decide the matter quite straightforwardly. Many instruments can be used to overcome the limits of perception. We also have a lot of techniques we can use to remove observational mistakes. A good example of this is provided by the N-ray controversy. Early in the 1900s, the physicist Prosper René Blondlot, whose name I'm almost certainly pronouncing incorrectly, this physicist claimed to have discovered a new type of radiation known as N-rays. Blondlot had fired X-rays through a quartz prism, which was known not to reflect such radiation. He had a detector off to the side which would produce an electric spark when radiation entered. And he noticed that the spark in his detector got brighter when he fired the X-rays at this quartz prism, suggesting that radiation actually had been reflected off the quartz. But this couldn't be X-rays, so he assumed that he discovered a new type of radiation which he called N-rays. Blondlot developed a different system for detecting N-rays. You're supposed to sit in a darkened room with a phosphorescent screen, and the screen lights up when hit with N-rays. Now, many scientists studied these N-rays and numerous papers were published. Various other means of detecting and manipulating N-rays were developed, and theories about them were proposed. But there was a problem. There were many scientists who just couldn't detect them at all. The problem was resolved by the scientist Robert Wood. Wood went to Blondlot's laboratory to observe his experiments, and while there he removed parts of Blondlot's equipment without telling him. Blondlot claimed to observe exactly the same N-rays as before. So it was perfectly clear that N-rays didn't really exist. It was a subjective phenomenon. Blondlot thought he saw N-rays being detected when in fact they couldn't possibly have been. So it was perfectly clear, that these weren't real. Here we have a case where scientists reported different observations. Some saw N-rays and some did not. But since the people who reported seeing N-rays continued to report them even when it was impossible for them to have been produced, this showed their observations to be untrustworthy. So we can overcome theory-ladenness using these kinds of techniques. It doesn't necessarily matter if observations are different if you have techniques for eliminating some of those observations. Now, there are other cases in the history of science that involve poor data that also don't seem to fit the Kuhnian model. A good example is the controversy in the late 1800s, after astronomers such as Giovanni Schiaparelli and Percival Lowell reported observing what seemed to be artificial canals on the surface of Mars. Here's a map of Mars by Schiaparelli showing the so-called canals. Many people took these canals to be evidence that the planet was inhabited by an advanced extraterrestrial civilization. Lowell believed that the canals represented an advanced irrigation system. Now, this turned out to be a complete mistake. There are very few features on the Martian surface that actually correspond to these canals. I mean, not only are there no advanced alien life forms on Mars, but this map is just completely wrong. The features that Schiaparelli thought he saw just aren't there. Now, this case should provide a perfect example for the Kuhnian for two reasons. First of all, there was widespread belief in extraterrestrial life at the time on both scientific and religious grounds. So most people would have expected that Mars was inhabited. Scientists would have been primed to see evidence of extraterrestrial life on Mars. There's a great book by Michael J. Crow called The Extraterrestrial Life Debate, which goes into the belief in extraterrestrial life at the time. It was very widespread, and there were both scientific and religious reasons for that. So the second reason is that telescopic images of Mars were very poor. So they provided very ambiguous information. Now, from the psychological studies of the new look psychologists, this is just the kind of case where we might expect theory-ladenness to be a problem. However, many astronomers were sceptical of the canals, and I think their objections are quite instructive. So, the astronomer Edward Maunder showed that dots seen at a distance appear as a straight line. So the apparent canals, he suggested, might just be an illusion arising from disconnected patches seen from far away. Similarly, the astronomer Vincenzo Cerulli argued that the moon, when viewed through low-power telescopes, also exhibits canal-like features, which through higher power telescopes can be seen to be just natural patches. So many astronomers at the time argued that the apparent canals were just illusions. Now the question is, did Lowell and his critics see different things? Well, Kuhn would say that Lowell saw canals, whereas his critics saw optical illusions, and in some sense this is true, but it also seems clear that Lowell and his critics shared a substantial base of observations. After all, Lowell's critics agreed that Mars, viewed through a telescope, appeared to show straight lines. The question was how these appearances are to be interpreted. So there was no disagreement about how Mars appeared. So even in this kind of case then, it's not really clear that we can find much support for Kuhn's approach. And I think we can give a more general argument here with a very similar model, so a similar moral. Consider again Kuhn's suggestion that looking at the bubble chamber photograph, the student sees confused and broken lines, the physicist a record of subnuclear events. Well, surely there's some sense in which the physicist also sees the same thing as the student. I mean, otherwise, how would she be able to teach her student how to read the record? The physicist can say, look at this bit here, and then she can explain how that bit is to be interpreted, and most of the time the student will understand her. So now imagine a different physicist who accepts a completely different physical paradigm. Well, she's also able to teach her students how to read the photograph in terms of her paradigm. So she must also see the same things as the novice student. But it follows that both physicists who accept very different theories share the same observational base that is neutral between their theories. This is the observational base that they each share with the novice student. Okay, so one final objection to theory-ladenness is given by James Bogan and James Woodward. They argue that the traditional dichotomy between theory and observation is misleading, and that we should really draw a tripartite distinction, theory, data, and phenomena. So we can think of data as being equivalent to observations. Suppose we're measuring the melting point of lead. We observe a certain number on the thermometer. Under standard pressures, it will be about 327.5 degrees centigrade. What we observe on the thermometer is a piece of raw data. Now, according to Bogan and Woodward, we don't test our theories against raw data. Instead, we use data to infer phenomena, where phenomena are defined as events or regularities or processes that are uniform in some kind of way. And so they allow for prediction and explanation. To use the example of lead, the phenomenon is that at standard pressures, lead melts at about 327.5 degrees C. This phenomenon is stable and uniform. Now, the data that support this phenomenon are variable, they're idiosyncratic. When we measure the melting temperature of lead, we will get various different readings for all sorts of reasons. Our reading will depend on the purity of the lead, on the workings of the thermometer, it will depend on the initial conditions in the experimental setup, and so on. There are a whole host of factors that affect the collection of data. We use the data to infer the phenomena. So how does this apply to theory-ladenness of observation? Well, the phenomena are themselves unobservable. We don't observe that lead melts at 327.5 degrees centigrade. This is inferred from the data. So the phenomena cannot be theory-laden. Of course, Theory is involved in inferring phenomena from data, but this is rarely the theory under test. So the reliability of the data and the existence of the phenomenon doesn't depend on any sophisticated theory, on any sophisticated paradigm. The procedures we have for ensuring the reliability of data are going to be things like statistical analysis and so on. So the data are not theory-laden either. So if we adopt this kind of view, then it looks like there's not really anywhere that theory-ladenness can get any purchase, or at least arguably. Bogan and Wood would argue that when we properly see how observations actually work in science, there's not really anywhere for theory-ladenness to be a problem. Okay, so let's move on to semantic incommensurability. The basic idea of semantic incommensurability is that the very meanings of terms in two different paradigms are different. A standard example is the development of physics from Newton to Einstein. We usually think of Newton as getting reasonably close to the truth, and we think of Einstein's relativity theory as getting closer still. Indeed, generally, Newtonian mechanics is sort of treated as approximating relativity theory in certain conditions. But Kuhn is quite sceptical of this. He thinks that actually there's a very substantial rift between the two theories, and that talking of Newtonian mechanics approximating relativity theory is just it's just a confusion. So think about the concept of space. Right, space is a central concept for both Newton and Einstein. Now, for Newton, space necessarily referred to something homogeneous, flat, with a Euclidean structure. So that's Euclidean geometry, and it's unaffected by matter. Furthermore, space for Newton is fundamentally metaphysically separate from time. So Newton conceived of space as a kind of stage, as it were, on which the events and processes of the universe are carried out. Space is not affected by the distribution of matter, and time ticks along independently. I think that's sort of the way you can think about it. Now, this picture is entirely rejected by Einstein. For Einstein, space and matter and time are inextricably intertwined. Indeed, in relativity, strictly speaking, we don't talk about space and time separately, but rather space-time as a single entity. The geometry of space-time is non-Euclidean. It curves. A large mass warps space, and time warps with it. So we get length contraction and time dilation. And as I've mentioned in previous videos, we get the fact that a large mass like the sun bends light. I mean, that's kind of an inaccurate way of putting it. What the sun actually does is it bends space itself, and light continues going on a straight line from its perspective, as it were. But because space is bent, it bends. So when we think about space as a general concept, it's quite clear that the concept used by Newton and the concept used by Einstein are very, very, very different. It's difficult to specify anything really that they actually have in common. So the very meaning of the term space has changed between the two theories. Similarly, other concepts like mass and force and so on are also defined very differently. So in the transition from Newton to Einstein, a whole battery of important theoretical terms change their meaning. To quote Kuhn, he says, "To make the transition to Einstein's universe, the whole conceptual web, whose strands are space, time, matter, force, and so on, had to be shifted and laid down again on nature whole." Now, I should note that Kuhn's view here assumes what's known as meaning holism, or at least some degree of meaning holism, which is essentially the claim that the meaning of a theoretical term or sentence is determined by its place in the theory as a whole. And certainly this seems plausible to at least some degree. If you ask what a term means, you generally cite other terms, and then those terms will themselves be defined by other terms still. Just look at a dictionary. And of course you have the same with theoretical terms in science. So for instance, the term energy has a very specific definition in physics. So this is Wikipedia's definition, just I quote Wikipedia. It says, energy is the property that must be transferred to an object in order to perform work on or to heat the object, and can be converted in form but not created or destroyed. Now, there's a huge battery, there's a huge background of theory being assumed here. What is work? What is heat? What does it mean to convert energy? What do we mean when we say it cannot be created or destroyed? Would it really be possible to understand what energy is without understanding contemporary physical theory? It seems like it just wouldn't make sense. Imagine if Aristotle was brought back to life and you had to explain to him what energy is, in the sense that it's used in physics. It looks like you're going to have to teach him quite a bit of physics before he's going to be able to understand, to even understand the meaning of the term. So basically, Kuhn is just saying that when we go through paradigm shifts, when we go through these major scientific revolutions, these major theory changes, the very meaning of the terms is going to shift radically as well. Now, this is often taken to have quite substantial philosophical consequences. Howard Sankey breaks down the consequences rather nicely. He says, the meaning variance of theoretical terms entails translation failure between the theories, which leads to content incomparability of the theories. So basically, the thought is that if the meanings of central terms vary, then we're not going to be able to translate from one theory to another. Scientists who adopt different paradigms literally talk past each other. So suppose the Einsteinian says mass changes with velocity, and the Newtonian denies this. Well, Kuhn would say they're not really disagreeing, because the term mass means something different for each of them, and so does the term velocity. So they're not asserting and denying the same proposition. It's just an equivocation. So we have this translation failure between the paradigms. The claims made by one paradigm are not really expressible in the terms provided by the other paradigm. So if we can't translate between two paradigms, it follows that the paradigms can't be compared. The adherents of one paradigm can't really even articulate what the adherents of the other paradigm believe. So they have no way to make a comparison. During crisis science, the debate between competing paradigms is not a genuine debate. And that's one of the reasons why you don't move from one paradigm to another by logic and experiment. So how might we respond to this idea? Well, first of all, I should say that this is a fairly extreme interpretation of Kuhn. Kuhn himself probably, he wouldn't have accepted that two paradigms are literally incomparable. But this is certainly what semantic incommensurability does entail, is that comparing two paradigms is not a straightforward matter. It's certainly not as straightforward as comparing two different versions of the theory in the same paradigm, or two hypotheses proposed in the same paradigm. But certainly a number of philosophers have taken Kuhn's ideas to entail some of these more extreme conclusions. So it's worth considering, does meaning variance lead to translation failure and so incomparability? Well, for one thing, we might question whether we might want to look at what theory of meaning we accept. I won't go into this in too much detail here, but generally philosophers hold that meaning has two components, sense and reference. The reference of a term or description is the object in the world that it refers to. The sense can be thought of as the way in which it refers. So consider Frank Zappa. There are various ways I might refer to him. I might say the composer of Joe's Garage, or I might say the father of Dweezil Zappa. These both refer to Frank Zappa. These two descriptions have the same reference, but they still quite obviously differ in meaning because they refer to him in different ways. So we would say that these descriptions have the same reference but different senses. Now this is important because it shows that just because the sense of a term varies across paradigms, it needn't be the case that reference varies across paradigms. Terms like mass and space had different senses for Newton and Einstein, but arguably they had the same reference. Now, of course, this depends on what exactly your theory of reference is. There are different views about this in the literature. If you go to my video, Scientific Realism, Pessimistic Induction, about 10 minutes in, I outline what's known as the causal theory of reference. This theory would allow the sense of a term to vary considerably while the reference stays the same. And arguably all that's needed for translation between theories, and so theory comparison, is sameness of reference, not necessarily sameness of sense. Theories of meaning aside, I think that there are some good general reasons to be sceptical of this link between meaning variance and translation failure. A good illustration of this is provided by anthropological studies of experiences of emotion in different cultures. The Ilongot are a tribe in the Philippines. The English term anger and the Ilongot term liget are applied to very similar behaviours, but they differ subtly in meaning. Liget is similar to anger, but it's a positive emotion involving feelings of passion, energy, perseverance and inspiration. Westerners, of course, tend to conceptualise anger as being something negative. So it seems that the meaning of emotion terms across cultures don't correspond in a one-to-one manner. The Ilongot, we might say, have a slightly different emotion theory to us, and perhaps this leads to different experiences of emotion and to meaning variance of emotion terms. But the thing to notice is that we know that liget differs from anger precisely because we can translate the Ilongot emotion language into English, and so we can identify similarities and differences. We know that the terms differ in meaning precisely because the English and the Ilongot emotion theories, as it were, are translatable. If we were unable to translate the Ilongot emotion terms, we would simply have to be agnostic about their meaning. We would not know whether the Ilongot had a word similar to anger. Indeed, we wouldn't know whether they had any emotion terms at all. We'd just have to do, further study on them. So the moral here is that this claim that meaning variance leads to translation failure just seems to rest on a fundamental mistake. In fact, identifying meaning variance in the first place requires that translation is possible. Translation failure undermines any evidence we might have for meaning variance, so it's self-defeating to use meaning variance to argue for translation failure. There might be some empirical support for this from the sciences themselves. David Hull, in his book Science as a Process, on page 495, reports on the basis of interviews with various scientists, and I quote, "Difficulty in understanding does not especially co-vary with differences in overall theoretical outlook." And this, of course, would suggest that holding different theories, different meanings of terms, doesn't tend to lead to translation failure. A final point is that in practice, meaning variance actually occurs all the time. It occurs even within the same theory. We often find when we examine the sciences that a single concept is associated with a plurality of meanings. And a great example of this is the concept of species. This is a central concept in biology, and yet different definitions have proliferated over the past few decades. I have a video, a couple of videos on this called the species problem. So if you want to learn more about it, go and watch those videos. I think it's a really interesting problem. What is a species? How should we define species? But there are various options. Here are just two of them. One is the biological species concept, according to which a species is a population of organisms capable of interbreeding that are reproductively isolated from all other populations. And then there's the ecological species concept, which holds that a species is a population of organisms that occupies a specific adaptive zone and that evolves separately from other populations. These are very different definitions, and the disagreement here is not merely semantics. These concepts cross-classify populations, and they give very different estimates of species richness. Jerry Kuhn and Alan Orr, in their Catalogue and Critique of Species Concepts, they note that applying different species concepts to birds of paradise results in anything from 40 to 90 species. So this is a substantial difference. Now, on the other hand, I think it's clear that the disagreement between different species concepts is not so great that we have to say that each species concept belongs to different paradigms. I mean, to accept, if you were to hold that, then you'd basically be saying that any disagreement whatsoever in science constitutes competing paradigms. Two scientists who agree on almost everything else could adopt different species concepts. So species, it seems, is a case where a term has substantially different meanings even within the same paradigm. Henry Taylor and Peter Vickers call this phenomenon conceptual fragmentation. And this is where a single term has distinct but closely related meanings and uses, and no particular meaning is taken to be the one correct meaning. They give 20 or so examples of concepts in contemporary science that exhibit conceptual fragmentation. I think it's quite clear that even within theories, terms have a variety of meanings. And actually, the same scientist, the same researcher might adopt different definitions for different purposes. Furthermore, even when we define terms precisely, they tend to fragment again as the science develops. So, to take species concepts, well, we might, for certain purposes, adopt just one. So, the word biospecies is used to refer to a population that meets the biological species concept. So a biospecies is an interbreeding population reproductively isolated from other populations. But the problem is that there are many different ways of understanding this criterion. So, for example, does the creation of a geographical barrier immediately produce a new species? Or should we say that two populations of the same species, if they would interbreed, were they to meet? I mean, there are lots of questions like that we can ask about this. And so evidently this biological species concept can be elaborated in different ways, and so it can fragment even further. So my point is that meaning variance is not something that occurs just between paradigms. It's ubiquitous. And obviously, nobody would want to claim that scientists working within the same theory face translation failure. So it seems that meaning variance perhaps isn't does not have such bad consequences. So that is incommensurability. I hope you found that interesting, and that's all for today. Goodbye.